today we'll look at a theorem which basically states that if we're in a Hilbert space and we have a subspace y and we have a point outside of this subspace, then there's a unique closest point. Okay, so now we prove existence. Suppose yn is a sequence in y, so that the norm of x minus yn converges to the infimum, the norm of x minus y prime, where y prime is in y. And we will define D to be this. Now, if we get a limit for the sequence, say y, then we would be done because we would have that x minus that limit y, norm of that would be D. Okay, so now since y is closed and h is of course complete, then y is complete. So if we obtain that yn is a Cauchy sequence, we obtain a limit. Okay, to show that it's Cauchy, note that the norm of a difference, so yn minus ym, is the norm of this difference, x minus yn minus x minus ym. And we will try to use the parallelogram law to bound this. So norm of x minus yn squared plus norm of x minus ym squared twice this is the norm of the difference, which is yn minus ym, norm of that squared, plus the norm of the sum, which is 2x minus yn plus ym squared. Okay, so this can be expressed as this whole thing squared, 4 times the norm of x minus the midpoint, which of course is in y, all this norm squared. So since this is in y, of course this is greater than or equal to norm of yn minus ym plus 4d squared. Okay, so putting this on the other side, we get that 2 times norm of x minus yn squared plus norm of x minus ym squared minus 2d squared is greater than or equal to norm of yn minus ym squared. So if n and m are large enough, we can make this as small as we want. So when n goes to infinity and m goes to infinity, this whole thing goes to 0, which implies that yn minus yn is Cauchy. So it has a limit. And as I said before, this implies that the norm of x minus this limit is D. So this finishes existence. Okay, now uniqueness in part 1 will follow from uniqueness in part 2. So I will just proceed to part 2. Let's prove existence. So suppose y is a minimizer of a distance from part 1. So this is D. Okay, now suppose x minus y is not in y perp. So this means that there is a y prime in y, so that x minus y dot y prime is not 0. Okay, so if this is called C, we know that norm of x minus y, cy prime is different from 0, and this is norm of c squared. So we can assume that this is x minus y comma y prime is in R. The thing is that this might be in C, so we'll need this to compare things in R. So okay, now let's look at the norm of x minus y squared. Since y is a minimizer, we know that this is less than or equal to norm of x minus y, lambda y prime squared. Now is equal to a norm of minus y squared plus lambda squared norm of y prime squared plus 2 lambda x minus y comma y prime. Of course, with lambda and r. Okay, and this implies that 0 is less than or equal to lambda squared times norm of y prime squared is 2 lambda minus y comma y prime. Now we will divide by modulus of lambda. So we get that 0 is modulus of lambda times norm of y prime squared plus 2 lambda times divided by modulus of lambda times this dot product. Okay, so now when lambda goes to 0, from the positive side, this is just 1, and this is this goes to 0. Oh, sorry. This goes to 0, and so this implies that this dot product is greater than or equal to 0. Now, similarly, we're taking the limit when lambda goes to 0 from the negative side. We get that this is minus 1, so norm of x minus y, comma y prime less than or equal to 0. So x minus y, comma y prime is 0, which is a contradiction with this. So this completes existence. Now, for uniqueness in part 2, suppose that x minus y1 and x minus y2 are both in y perp. And of course, y1 and y2 are in y. Now subtracting these, we get that y1 minus y2 is in y perp, and I guess subtracting these, we get that y1 minus y2 is in y. And so together these imply that y1 minus y2 is 0, so y1 is y2. So this proves uniqueness in part 2. Now, why does uniqueness in part 1 follow? Notice that for existence, in part 2 we showed that any minimizer in part 1 is also a y that satisfies the orthogonality relation in part 2. So if we have y1 and y2 such that these norms are both d, then we get that this is true. So y1 is equal to y2, so we also get uniqueness for part 1. So this concludes the proof.